All right, continuing onward with our AC circuits here, we want to look at something else. How about we look at an inductor connected to an AC source potential? We can draw that out again. Got a little AC source potential, delta V of T. And then we've got ourselves a nice inductor there, has some inductance L, that's a great. And what it's also going to have is some self-induced EMF, E sub L, great. And what do we want to do with this? Well, again, we want to utilize Kirchhoff to go ahead and give us some sort of expression to go with, and then proceed onward from there. So yeah, this alternating potential difference going back and forth, driving the current in opposite directions, that way, then that way, that way, then that way. Let's just go ahead and again and say we're looking at a point in time when the current's kind of going around like this. So in an inductor, the plus side and the minus side are oppositely corresponding to the current. It's not a resistor, this is an inductor that produces a self-induced EMF as the current goes through it. So if this is minus, this is plus. So when we write out by Kirchhoff, we have that delta V of T plus E sub L, and this is going to be varying with respect to time too, E sub L of T has to be equal to 0. Going around this way, plus to minus, excuse me, minus to plus to minus across that way, minus to plus, minus to plus. So what do we do with this? Well, we know that the self-induced EMF is equal to negative L di sub L, so we know that we're talking about the current through the inductor, di sub L dt. So there's the self-induced EMF. And thus we've got ourselves delta V of T minus L di sub L dt must be equal to 0. So that's what we've got going on. And like we did before, we can go ahead and start moving some things around. Use blue, but it's okay. We'll switch colors here. So we're going to write this out then as delta V of T is equal to L di sub L by dt. All right, that sounds fantastic, right? So again, what we want to be able to get out of this is how does the current vary with respect to time? We already know how this varies with respect to time. This is delta V max sine of omega t, right? So I'm going to move some stuff to different sides here a little bit. Switch this over on this side and move that over there, and divide both sides by L. We can write this. di sub L by dt must be equal to delta V of T divided by L, which is delta V max times the sine of omega t divided by L. So there we go. We've got ourselves the sinusoidal variance regarding the source potential, the inductance of the inductor, and the time rate of change of the current through the inductor. That's the correlation that we have here. So what are we going to do with this? We still want to know, what is I of t? How do you get I of t? We'll go ahead and multiply both sides by dt and do some integration. So let's go ahead and move this on over up here, multiply both sides by dt, and we're going to have di sub L is equal to, I'm going to leave a little bit of room here, but we've got ourselves a delta V max divided by L times the sine of omega t dt. All right, that looks pretty good there. So what are we going to do with this? Well, you guessed it, we're going to go ahead and integrate both sides. Fantastic. All right, so just continue on with this. Integral of di. This is going to give us I sub L of t. And that will be equal to delta V max divided by L, integral of the sine of omega t dt, where we've got the integral of the sine of omega t is going to be equal to 1 over omega times the cosine of omega t, negative sign out in front. Derivative of sine positive, integral negative, yes. So this goes over to negative delta Vmax divided by L omega times the cosine of omega t. All right, and that's our I of t right there. So what do we have here? Well, we're going to write them both out. We've got ourselves I sub L of t is equal to this negative delta Vmax divided by L omega times the cosine of omega t. And we've got delta V of t, the source potential, is equal to delta Vmax times sine of omega t. Well, look at this. This one's varying as cosine, this one's varying as sine. There's a negative sign out in front of this one, not in front of that one. They're both varying at the same angular rate, omega. That's great. So they're in sync in terms of their variations that are occurring, but they don't start in the same spot, in the same manner. That is, when this one says 0, this is not. And vice versa, when this is 0, this is not. So they're out of phase with one another, not in phase. Well, that's not the case that we had with the resistor, right? The resistor was, the current through the resistor was in phase with the potential difference. Not here, not here. So what are we going to do with this? How can we see what this phase difference is? So, let's see, we've got a negative cosine there, and we want to turn that into a sine. So we can write that negative cosine of omega t is equal to sine of omega t minus pi over 2. Sine of omega t minus pi over 2. And make sure that that's the case. Say if we said that omega t was equivalent to 180 degrees, the cosine of 180 would be equal to negative 1 times negative would give us positive 1. If omega t was 180 degrees, we would have 180 minus 90, which would give us the sine of 90, which would also be positive 1. So you can always go back and check. Sometimes I mix up the plus and minus, but that's a nice trigonometric correlation there, which then allows us to rewrite this current as a function of time in terms of sine. So now we can write that I sub L of t is equal to, the negative cosine is going to be replaced with this, and we've got ourselves delta Vmax divided by L omega times the sine of omega t minus pi over 2. So what happens if we plot this on out? So this is a nice way of writing it, because we can see something about this. So plot these out. And do a blue and red and purple share. So I'm going to plot out this first, this I of t, which is equivalent to that. So negative cosine is its variance. So it starts down here, goes up, goes down, goes up, goes down. So this is going to be our I of t. And that's the same as this function right here. And then we've got ourselves delta V t. Well, you know how that goes. It starts at 0, goes up, then down. When it's at its max, the way cosine and sine work, right? It's going to be there, 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 and crosses here. So I make these all a nice continuous wave, and that's our cosine. I'm going to try to do the best that I can here. Something like this. This is our sine wave, which would be delta V of t. So what do you notice about this? Yeah, they start in different spots, and they're never having the same corresponding maximum or minimum simultaneously, or 0 point simultaneously. When this is 0, the other one's a max. Or when it's 0 here, it's negative of the max. And likewise for the current 0, potential difference is a max, either positive or negative. So what do we have? Well, this is a phase angle right here. This just ultimately says that there is a phase difference between this function and this function. This one is pi over 2 radians behind this, negative pi over 2. So in this particular case, we have that for an inductive circuit, the current through the inductor is lagging the potential difference of the source potential by 90 degrees. In this case, C-U-R-R-E-N-T, current lags potential difference by 90 degrees, or pi over 2 radians. So a way to visualize this is with what are known as phasor diagrams. So phasor diagram is just a nice way of corresponding the variation in these values, the current and the potential difference, in terms of looking at the projection of an arrow that's rotating around a circle onto the y-axis. So this is what we've got. Phasor diagrams look at projection of an arrow having max value projected onto the y-axis for the instantaneous value as the arrow rotates in a circle with an angular velocity omega, which that omega is equivalent to the angular frequency of oscillation of the source. So this is what we've got with this. So, let's start this. I'm going to take this circle here. Great. We've got this. This is the y-axis here. This is like an x-axis there. And then we've got these phasors, which are these arrows that are rotating around the circle counterclockwise at an angular speed of omega. So, at t is equal to 0, what is the value of the source potential? The value of the source potential is this, delta V max times the sine of omega t. If t is equal to 0, well, that corresponds with being along the x-axis, 0 radians or 0 degrees or 2 pi radians or 4 pi radians for that matter. And it just has a value equal to 0, but its maximum value is delta V max. So we've got this. Got this arrow that is representing, has a length that corresponds to delta V max, and its projection onto the y-axis gives us what its instantaneous value is. If we project this on the y-axis right now, its instantaneous value is equal to 0. All right, what about the current in the inductor? Well, the current in the inductor is going like this, negative cosine omega t, and we've got this delta V over L omega, which we could just say is I max. So I'm going to make that little portion right here. Delta V max over L omega is equal to I max. We'll come back to that, but that's just to make this a little bit easier to draw out. And at t is equal to 0, we've got the cosine of 0 would be equal to 1. Then there's a negative sign there, and we would have this. I max. Well, let's point it straight down. Its projection onto this y-axis is its whole value here, which is this delta V max divided by L omega, which is equivalent to I max. So what we have with these phasor diagrams now is that these rotate around with an angular speed of omega, which again corresponds to the angular frequency of the oscillations themselves. So as time goes on, this angle between these two is preserved. That's the phase difference between them. The current is behind the potential difference, and we can draw another diagram to kind of get the idea of the projections here. So time proceeds onward a little bit, and at some point, hey, here is delta V max, delta V max. Well, what is its projection onto the y-axis? Its projection onto the y-axis would just be this right here. This would be delta V at that moment in time that this has that corresponding direction or angle that goes back with what is omega t. There's its value there, delta V of t. Well, as this one rotates, so does the current. The current rotates, they have the same correlation. They stay 90 degrees apart. So the current, so this, and its projection onto the y-axis, so like this. That is I sub L t. That is the current through the inductor at that specific moment in time. And then this continues rotating, and you can really say at any moment in time then what the corresponding values are by looking at the projections onto the y-axis. And that's just using some things with sine and cosine, right? But phasor diagrams, they're nice to be able to look at what's leading, what's lagging. The potential difference is ahead of the current, or you can say the current's behind the potential difference. Current lags the potential difference. That's what we say there. So that's what we got with phasor diagrams. We'll go back to the resistor here in a little bit, but right now I want to look at this. Look at this. We've got the maximum current in this inductive circuit is the maximum potential difference divided by the quantity of the inductance multiplied by the angular frequency. What does that mean? Well, let's think about this. Let's look at Ohm's law, just for instance, right? For Ohm's law, we've got that I max is going to be equal to delta V max divided by R. Well, I itself has to have units of amps, or whatever unitization you're using. The units of this and the units of this has to be the same. Units of the potential difference have to be the same. So what's left? Well, that says that the units of R have to be equivalent to the units of L omega. That seems interesting, right? This L omega has units of ohms. is it's acting like a resistance in a sense. Has a resistance-like quality to it that ultimately dictates what the maximum output is, current-wise, in the circuit. Potential difference, get the potential difference divided by this amount, which depends on the inductance and the angular frequency, determine what the maximum current is. It's a resistive-like quantity. So what we'll do here is we define a new quantity, call it something else, but ultimately have the idea that it's coming from this. So let us define quantity called inductive reactance. I always love that name, inductive reactance, like a cool band or something. Anyways, inductive reactance, and this is chi sub L. Kind of looks like an X, it's a Greek letter chi. Anyways, chi sub L, and we're going to say that chi sub L is equal to L omega, so that we can write this. Delta V max is equal to I times chi sub L. And max times chi sub L. Or that I is delta V max over chi sub L. Right. And sure, doing that part right there. All right, so that's good. This is like sort of like an Ohm's law. Delta V equals IR, but instead of R, it's the inductive reactance. And that's how we get the correspondence, again, between the maximum values. So if we come back over to what is I max, well, I max is delta V max divided by L omega. And well, that just gives us this again. Anyways, that's what we get out of that. Fantastic. Resonance, no, we don't care about that right now. All right, so we can move on a bit here and start looking at some other things. One thing to note, this is quantity there. Thing to note is you can also look at the Phasor diagram for resistors. For a resistive circuit. We have it there in phase with one another, so it ends up being a really easy Phasor diagram. But ultimately, I'll just draw one out. We've got jumps off of it here. So this would be our, say, delta V max. This would be I max, and we can look at their projections onto the y-axis at any given moment in time and say, okay, there's I sub R of t, and projection of the other one. This one's just black here. All the way up would be delta V t. And this would spin around again with some constant angular rate omega, and they're always in sync. When one's 0, the other's 0. When one maxes, the other's a max, and that. Much different from how the inductive circuit works. All right, so lastly, not really lastly, but another thing we want to look at is capacitor and AC. Cool. I just realized I spelled that wrong. Full inversion there, that should say AX. IS, not ASICS. Anyways, mean spelling sometimes, going. Little spell check on the whiteboard. One of these days, maybe you invent something. Anyways, here we go. Capacitor and AC. Ooh, what's that gonna be like? Well, let's check it out. So again, we've got ourselves a nice little source potential here, delta V T time varying. We've got ourselves a capacitor. And we've got ourselves in some aspect of the current going around a certain direction at a certain moment in time. And when it's going this way, we'll have this is the plus, that's the minus, and this will be the plus minus there. And we've got ourselves some delta V sub C of T. We're going to go from plus to minus to across it, and we will have ourselves, again, delta V sub C of T. Could be written in terms of the charge accumulation and potential difference. Charge per unit potential difference. Oops, that's delta V sub C. Already, from the definition of capacitance, I should say, we've got Q of T divided by delta V sub C of T. So there's our definition of capacitance. From this, we've got ourselves that delta V sub C of T is Q of T divided by C. All right, so then we go ahead and go around this. We're going from minus to plus, then plus to minus. So we've got ourselves by Kirchhoff. That delta V of T minus Q of T divided by C has to be equal to a 0. Fantastic. So what do we do with this? The same thing that we've done before here. We go ahead and say, well, then delta V of T has to be equal to Q of T divided by C. We know that delta V of T is equal to delta V max times the sine of omega T, which must be equal to Q of T divided by the capacitance C. All right, we can go ahead and solve this out with Q of T. The charge accumulation of the plates of the capacitor as a function of time is equal to C delta V max times the sine of omega T. But though we're interested in the charge accumulation as a function of time, it's continuously changing, right? It's not like it's charging up to some maximum amount that's terminal or discharging to some 0 that's terminal. It continues to accumulate charge and then sweep the charge over here, then back, then back, then back, then back. And what does that substantiate? It substantiates an ever-changing current, right? As long as the source potential keeps alternating, the current keeps alternating to continuously charge, discharge, then recharge in the opposite polarization, the capacitor itself. So what we're more interested in, the second time, is what is the current in the circuit here? So we're going to say not the current through the capacitor, because that makes no sense, but the current due to the capacitor in the circuit. We're going to say I sub C of T. Well, how are we going to get that? What's the definition of current? Time rate of change of charge. That's right. So we've got d by dt of Q of T. Well, look at that. We've got a Q of T. So we can go ahead and say then that I sub C of T is equal to Well, d by dt of q of t, which is d by dt of this. D by dt of the quantity c delta v max times the sine of omega t. All right, so we've got ourselves a sine there. What is the derivative of sine omega t? That's just going to be omega cosine omega t. The derivative of sine is positive cosine, positively. And what do we get out of this? Well, we've got then that I sub c of t is going to be equal to c omega delta v max. Actually, I'll just put the omega out front. Omega c delta v max times the cosine of omega t. There's the current as a function of time. Again, what do we notice? Delta v itself is equal to delta v max times the sine of omega t. Uh-oh, sine versus cosine, they're not in phase with one another. Once again, similar to what we had with the inductive AC circuit. Capacitive circuit has the same sort of aspect. They're not in sync. They fluctuate in sync, but they don't start in the same way. So there's a phase difference between them. Not in phase. So how are we going to resolve this out? Well, again, let's try to rewrite this cosine in terms of sine. And we've got the cosine of omega t is equal to the sine of omega t plus pi over 2. Negative cosine was negative pi over 2, positive, positive. Making sure equivalent 180 would give us negative 1. Equivalent 180 plus this would be 270. Sine 270 is negative 1. Boom. That's the correct correlation there. So all said, we've got ourselves that the current in this capacitive circuit as a function of time is equal to omega c delta v max multiplied by the sine of omega t plus pi over 2 radians. So plus pi over 2, the current is ahead of the potential difference by pi over 2 radians. Current leads the potential difference by pi over 2 radians. What can we do with this? Well, a couple things. Let's start by drawing out a little phasor diagram. Why not? So something to note here, coming back with this, we can write this as I sub c of t is equal to I max times the sine of omega t plus pi over 2, where I max must be equal to this omega c delta v max. All right, and then we can go ahead and do a little phasor here, different colors, and so again, start this at some moment in time. I want to start it at t equals 0. That would be fine. At t equals 0. This is along the x-axis, 0 degrees. This would be along the y-axis at 90 degrees. So we could have this. Here's our delta V max, and this, which we could have as I max. And what's going on with these? Yeah, everything's rotating around a constant angular rate omega. There's a nice 90-degree angle in between I max and delta V max, or I and delta V, I should say. And as this rotates around, as time continues forward, the projections of these phasors onto the y-axis give the instantaneous values. So at some time later, we could have something like this delta V max and I max rotate like this, not quite big, I max. And then the projections of those onto the y-axis would give us the corresponding values. This would be I sub c of t at that moment in time. And this would come over here, go all the way up, and be like this. This would be delta V of t at that moment in time. The main thing is current leads by 90 degrees or 2 pi radians, and that's how the current in the circuit works with respect to the potential difference. They're not in phase. So again, what else could we do with this? Well, as we've noted here, I max is equal to omega c times delta V max. Well, what's this all about? Well, let's go back to Ohm's law again, shall we? We'll say that the units of all of this, omega c delta V max, have to be equal to current, units of current, amps, right? The units of I max must be equal to the units of omega c delta V max. Well, what is this omega c then? What happens if we go ahead and say something like let chi sub c be equal to 1 over omega c. We're going to call chi sub c to c, capacitive reactance. Chi sub c, capacitive reactance, 1 divided by omega c. Why do we want to do that? Well, now we can write this as being equal to I max is equal to delta V max divided by chi sub c. Chi sub c has to have units of ohms. That's right. Not omega c though. Here now, chi sub c has units of ohms. Just like chi sub L did, which we've erased, but chi sub L was equal to omega times L. A little bit different here, right? To make things work out. So we've got an ohms-like law behavior here, where chi sub c, or 1 divided by omega c, acts like a resistance, in a sense. We don't call it resistance because it's not a resistor, it's due to a capacitor. So we call it capacitive reactance. It has this resistive-like behavior that gives a correlation between the maximum potential difference and the maximum current that depends on what is the angular frequency of the oscillations and what is the capacitance of the system. Fantastic. Some pretty good stuff right there. Love it. Love it. All right. So at that, we're in a position where we can start kind of putting some things together and looking at how it all comes to play. Because realistically, we don't generally stick just a resistor or just a capacitor or just an inductor in a circuit. Maybe the circuit has some essence of all of them. Not necessarily. Could just be a purely resistive circuit, but generally you don't just stick in a capacitor without some resistance. There's resistance, and every circuit has some amount of inductance as well. So what we're going to look at is what's known as RLC circuits. RLC circuits, not in DC though. This is an AC RLC circuit. So we looked at RLC a little bit with discharging a capacitor that's fully charged. There's a resistor in the circuit. No source potential though. This one's driven source potential, sinusoidally driven, and we're going to take a resistor, a capacitor, a resistor, inductor, and a capacitor all in series with one another. So we'll be doing that here momentarily. We'll make some more room with this, and we'll do just that. Fantastic.